Hi everyone, and welcome to our week on water. This week we're going to talk about chemistry concepts such as molarity, which is a term for concentration, polarity, which is important because water is a polar molecule, and we're also going to talk about concepts of water and the world. So we're going to go ahead and get started here. First of all, I want you to understand that water is a very limited resource in our world. If you look at most of the water in our world is actually salty water, about 97%. And then from that 2.6% here, that's fresh water, most of that fresh water is stored in ice caps and glaciers, so it's pretty much inaccessible. And then you have another 0.592% that is stored in groundwater. And you're left with 0.014% that is readily accessible. That's your lakes, soil moisture, your atmospheric water vapor, rivers, and life. So the vast majority of the water is not accessible. So some terms that you should be familiar with, I'm going to go over them with you, I'll do it through talking about the water cycle. So here you have a diagram where basically you have evaporation, right? So the water evaporates and goes into the air and it comes back down in the form of precipitation. And precipitation can be snow or water. And basically that water goes down the hill and we call that runoff. And that runoff can go on the land and into the streams and lakes. And a term for that is watershed. So wherever runoff occurs into a certain stream or lake, it's a watershed. So when you hear watershed, don't dump waste here because it gets into our watershed, meaning that when it rains, whatever you dumped on the ground will get mixed in with the water and run off into the rivers, lakes, or streams in the region. And so it's part of a watershed. Right, the other term you should know is aquifer. Aquifer is just a fancy way of saying groundwater. It's the water underground. So what happens when it rains, that water seeps into the earth until the water hits a point where there is a non-permeable layer such as clay, and the water can't go down any further. And the water level will continue to rise. And what this water table just indicates the area between the region that's filled with water, which is your saturated zone, and the area above that, which is your aerated zone. Aerated just sounds like air, so there's air pockets in it. It's not fully saturated with water. So this water table term is very important because when we pull out too much water from, pumping the water out of the aquifers, the water table starts to drop. Okay, that water table can drop. Another term is confined aquifer. So if you notice this second aquifer here, it's actually on top of it is a non-permeable layer, and below it is a non-permeable layer. So this water is trapped here, and it only can basically get filled up in what we call this area called the recharge area. So the water can fill that aquifer in a very limited region, and sometimes it takes hundreds or even thousands of years to fill up some of these aquifers, especially the confined ones. So if you put a well, they call this an artisan well because this water is hard to access. Alright, so if you put a well here and pump up the water, it may never refill in our lifetime. Another term is the rain shadow. We are familiar with this concept in California. So basically you have the ocean and you have warm, moist air blowing in from the ocean. All that warm, moist air goes up a hill or a mountain. And as the air goes up the mountain, it gets colder and colder and colder until it gets so cold that the rain actually comes out of the air as either the water comes out of the air as either rain or snow. And then when that air continues on down the mountain, on the other side, pretty much most of the water is gone at this point. And as you go down the mountain, the the air is getting hotter and hotter because you're going down back towards sea level where it's warmer. And so you at this point have dry air and no rain, and we typically see deserts. So here's the Sierra Nevada. This is one of the largest mountain ranges we have. And here's the ocean. You have all that warm, moist air coming over. See this green region? Then you reach the Sierra Nevada, and then what's beyond the Sierra Nevada? Desert. So that's your rain shadow. Since water is such a limited resource, we're actually starting to see global conflicts. This map shows the red regions, meaning areas that have high stress for water or global conflicts, and then the blue region means none. If you look at the United States, it's our region that is in high conflict for water, as well as you can see North Africa, the Middle East, and parts of Asia and Australia. We are starting to see a groundwater depletion problem here in California and the southwest of the United States. For example, the Ogallala, that's the world's largest aquifer, is right here. It's in this red center. And this is one of those confined aquifers. So once that water is removed, it will not refill. And so these red regions are just meaning there's too much withdrawal from the water. And what happens when you have too much withdrawal, you can get things such as subsidence and sinkholes. Here's an example of subsidence. This is the San Joaquin Valley. There's a light pole here, or a, not light pole, what do you call that, electrical pole. So in 1925, so in 1925, you can see the level up here. You can see the level in 1925 where the land used to be. So if that man was standing in 1925, he would have been standing right there. And as the water is getting pulled out of the earth, the soil sinks down because the water is not holding it up anymore. And so in 1955, right here on the map or the image, this is where the land was. And now at this point in the picture, 1977, this is where the land was. We have found that parts of LA have already sunk as much as 25 to 30 feet. So this is even happening nearby us and locally. Sinkholes is a similar concept. It's just the type of soil they have. And what happens, the underground cavern for where the aquifer was collapses, and it just sinks. So if there's a car or a house there, it just swallows it up. This is more common in Florida. So not only is water a limited resource, the fresh water that we do have is often polluted. According to the World Health Organization, 3.4 million premature deaths occur each year from waterborne illnesses, 1.9 million from diarrhea, and in the U.S. it's estimated that there's about 1.5 million illnesses per year. And in terms of the water, the major rivers, about half the major rivers are heavily polluted. And if you look at the developing versus developed world, and this is access to safe drinking water, where the blue indicates 100% access. So here's the United States and Canada, you have pretty much 100% access to safe drinking water. While other regions such as China and India, you're looking at between 75 to 90% have access. And part of this is because only, for example, in China, 10% of the sewage is treated in China. The rest of it's just dumped into the rivers. And places like Africa, you're looking at less than, even in some regions, less than 25% of the population have access to clean drinking water. And when we talk about pollution, there's two main sources. You have point and non-point. Point is where you basically can look at a pipe. For example, right here is a point source. This is a wastewater treatment facility. You have a pipe. You can actually see that this factory here is another example of factory. You can see these pipes are dumping waste or chemicals right into the river. That would be a point source. You can actually point at that pipe and say, hey, this is the pollution. That's easier to control in the developed world. This is typically heavily controlled. Non-point sources are much, much more challenging to control, and we still in the developed world have a hard time controlling this. And basically it's just runoff. You're looking at runoff. So you have urban streets, suburban areas, cropland, animal feedlot, rural homes. All of those things have pollution on the land that gets there for various reasons, such as pesticides, fertilizers, oil, cleaning supplies, whatever. All of that stuff, when it rains, it goes into our rivers, which also gets into our oceans ultimately. So here's an example. You see these oil all the time on the road. There's a drain. That drain goes to our rivers. It goes to our oceans. 50 to 90% of the oil in the ocean comes from land runoff. And you can actually see what runoff looks like from space. This is a NASA image of the Mississippi River Delta. All of this stuff here is just runoff. It's a mixture of whatever was on the land. It could be soil, whatever chemicals were on the land, including the oil. And this is actually devastating to sea life or ocean life because the majority, about 75% or more of ocean life, is near the coastal regions. And finally, the last term I really want you to know is bioaccumulation and biomagnification. Bioaccumulation is just like it sounds. It's you're accumulating stuff into life, right? That's bio is life, accumulation. So for example, here is a toxin. This is PCB, is in the water here. It has a concentration of 0.000002 parts per million. It gets bioaccumulated by the phytoplankton. They eat it or drink it, whatever. It gets into their bodies. Now the next term is biomagnification. So these phytoplankton now have 0.0025 parts per million in their bodies of this toxin. And then it goes up the food chain. So the zooplankton eat the phytoplankton, and now they have a higher concentration of 1.123 parts per million. Then the rainbow smelt eat the zooplankton, and now they have a more higher magnification of that pollution as 1.04 parts per million. The trout eat the smelt. You have 4.83 parts per million. Finally, the herring gull eats the trout, and you have 124 parts per million. And then those herring have their babies, their eggs, and those eggs are now 124 parts per million of, or have 124 parts per million of PCBs. And this is toxic to the eggs and to the babies. And it can actually decimate the bird population in these regions. Now, these toxins get into our environment in a variety of ways, right? They can get in from human sources such as coal burning plant, incinerators, cars, a variety of ways. And they can basically get swept into the air from the gases. They can come down back onto the water through rain or snow, which is precipitation. Or you can also get wind, which just takes it away, and you can get what we call deposition. That could be your dry, so instead of mixing with water and coming down as rain, it can actually come back to the earth as deposition, just dry chemicals. And that can get, again, into your rivers and lakes through runoff. And this would be an example of mercury. Mercury you get from fossil fuel burning. Mercury gets into our water. And mercury is highly toxic. Actually, it's a developmental. It causes developmental issues within the baby while it's in the mother. So they actually recommend that pregnant and breastfeeding women check mercury levels in fish because of biomagnification and bioaccumulation of mercury in the ocean and rivers. Alright, so that is everything for now. I hope you enjoy this module, and I will see you guys later. Bye-bye.